What if I told you that the galaxies you're about to see tonight began sending their light long before Earth even existed? Billions of years ago, when the universe was still young, when the very first stars were beginning to ignite, and when no one could have imagined that one day we would be here watching them. Tonight, we're going to travel to the most distant, the oldest, and the quietest corners of the universe. So just sit back, slow your breathing, and let yourself drift along with the journey to a place where time itself almost looks like it's just beginning. Take a slow breath and imagine looking up at the night sky, where the faintest glimmers of light may seem quiet and distant. To the naked eye, they might appear like tiny stars scattered across the darkness, but many of those gentle points of light are something far greater. They are entire galaxies, vast cities of stars so distant that their light has been traveling through space for billions of years before finally reaching us tonight. When we look at these distant galaxies, we are not simply observing objects that are far away. We are looking backward in time. Light does not move instantly across the universe. Even though it travels faster than anything else we know, the distances between galaxies are so enormous that the journey can take unimaginable lengths of time. This means that every distant galaxy we see is actually showing us what it looked like long ago, when the universe itself was much younger than it is today. In a quiet sense, the sky becomes a kind of archive. Every photon carries a message from the past, a message that began its journey long before our planet formed. Some of the galaxies we observe tonight were already shining billions of years before the Earth even existed. When their light first started traveling toward us, our solar system had not yet taken shape, and the Milky Way itself was still growing and changing. During those early ages, the universe was a very different place. Galaxies were smaller and often more chaotic than many of the graceful spirals we see today. Gravity was constantly pulling matter together, guiding enormous clouds of gas toward one another. Within those clouds, the first generations of stars began to ignite, lighting up the young cosmos. These early stars were powerful forges of creation. Inside their blazing cores, simple elements such as hydrogen and helium were transformed into heavier elements like carbon, oxygen, and iron. When those stars eventually reached the ends of their lives, many exploded in brilliant supernova events, scattering those newly created elements out into the surrounding space. Those scattered atoms would eventually become the raw materials for planets, oceans, and even living things. In that sense, the distant galaxies we observe today reveal the deep origins of everything familiar to us. The atoms that make up our bodies were once forged in stars that lived and died long before our world ever existed. Astronomers often point powerful telescopes towards small, seemingly empty regions of the sky and allow them to observe for many hours. Slowly, the darkness begins to reveal its secrets. Faint smudges of light appear one by one, each representing a galaxy that may contain billions or even trillions of stars. What once looked like empty space gradually transforms into a crowded cosmic landscape. Thousands of galaxies can appear within a patch of sky no larger than the width of your fingertip held at arm's length. And as we continue drifting deeper into this calm ocean of distant light, another quiet truth begins to emerge. The universe is not sparsely decorated with galaxies. It is filled with them almost everywhere we look. Once you begin to notice how many galaxies fill even the smallest patch of sky, the universe starts to feel very different. What once seemed like quiet emptiness slowly reveals itself as an enormous landscape filled with structure, motion, and history. Every direction we look contains countless galaxies, each one carrying its own story about how matter gathered together in the early universe. Astronomers have discovered that these galaxies are not scattered randomly like grains of sand. Instead, they form vast cosmic patterns shaped by gravity over billions of years. When scientists map the positions of millions of galaxies, a remarkable structure begins to appear. Galaxies collect along enormous filaments, stretching across space like delicate threads in a gigantic cosmic web. Between those filaments lie immense regions called cosmic voids. These areas contain far fewer galaxies and appear almost empty compared with the crowded strands of the web. If you could step far enough away to see the entire structure at once, the universe might resemble a glowing network of light, with galaxies tracing out the invisible architecture of gravity. The reason these structures formed goes all the way back to the earliest moments after the universe began expanding. In those first fractions of a second, tiny variations in density were scattered throughout space. Some regions contained just a little more matter than others. Over immense periods of time, gravity slowly amplified those differences. Regions with slightly more matter began pulling in additional gas and dark matter from their surroundings. Bit by bit, these regions grew denser. Clouds of hydrogen gas collapsed under their own gravity, eventually igniting the first generations of stars. As more stars formed, small groups of them gathered into the earliest galaxies. Those early galaxies rarely remained isolated for long. In the crowded young universe, gravity frequently pulled them toward one another. Sometimes they passed nearby, tugging on each other with tidal forces that stretched their shapes. Other times, they slowly spiraled together in long cosmic dances that lasted millions of years before finally merging into a single larger galaxy. These encounters played a major role in shaping the galaxies we see today. When galaxies merge, their stars usually pass by each other without collision because the distances between stars are so vast, but their enormous clouds of gas behave very differently. Gas clouds can crash together, compressing and heating as they collide. That compression often triggers intense bursts of star formation. New stars ignite rapidly across the merging galaxies, lighting up the system with brilliant blue clusters. For a time, the galaxy becomes a busy workshop of star creation, converting huge amounts of gas into new generations of stars. Over many billions of years, repeated mergers can transform a galaxy completely. A calm, rotating disk might be stirred into a thicker shape, while multiple smaller galaxies might combine to form a much larger one. In this way, galaxies grow not only by forming new stars, but also by gathering and absorbing their neighbors. When we observe distant galaxies, we often see signs of these dramatic encounters. Some appear stretched into long tails of stars and gas. Others show distorted shapes or multiple bright centers where two galaxies are still in the process of merging. These unusual shapes remind us that the universe has never been perfectly calm. Even the most beautiful galaxies we see today were shaped by long histories of interaction, collision, and gradual transformation across cosmic time. As astronomers continued studying distant galaxies, they began noticing something even more curious about the light arriving from the farthest ones. Many of these galaxies did not appear in the bright blues and whites that young stars usually produce. Instead, their light often looked stretched toward deep shades of red. At first glance, this might seem like a simple change in color, but in reality, it reveals one of the most fascinating properties of our expanding universe. To understand this effect, it helps to imagine light as a series of waves traveling through space. These waves carry energy from distant stars across unimaginable distances until they finally reach our telescopes. But the universe itself is not static. Space has been expanding ever since the earliest moments after its beginning. As that expansion continues, it slowly stretches the waves of light traveling through it. When light waves stretch, their wavelengths become longer. Longer wavelengths correspond to redder colors. This phenomenon is known as redshift, and it acts like a cosmic fingerprint that tells astronomers how far away a galaxy is and how long its light has been traveling. The farther a galaxy lies from us, the more the universe has expanded while its light was on its journey. As a result, the light becomes increasingly stretched, shifting further into the red and even beyond the visible spectrum into infrared wavelengths. This is why many of the most distant galaxies cannot be seen clearly with ordinary optical telescopes. To observe these ancient galaxies, astronomers often rely on instruments designed to detect infrared light. These observatories can capture the faint glow of stars whose light has been traveling across the expanding universe for billions of years. With these tools, scientists can study galaxies that existed when the cosmos was only a fraction of its current age. By measuring redshift carefully, astronomers can also build a timeline of cosmic history. Galaxies with small redshifts are relatively nearby and show us the universe in its more mature stages. Galaxies with large redshifts reveal what the universe looked like when it was much younger, during an era when galaxies were still forming and evolving rapidly. This method allows scientists to compare different eras of the universe within the same observations. In one deep image of the sky, some galaxies may appear as well-formed spirals with organized structures, while others look small, irregular, or clumpy because we are seeing them during their earlier developmental stages. In a sense, the universe provides its own historical record. Light from different distances acts like pages in a vast cosmic book, each page describing a different moment in time. When astronomers observe these galaxies together, they are reading that history across billions of years. And sometimes, the universe provides an unexpected helping hand in revealing its most distant secrets. Massive objects in space can bend and magnify light in ways that allow astronomers to see galaxies that would otherwise remain hidden, far beyond the reach of our instruments.
Sometimes the universe itself becomes a natural telescope, quietly helping astronomers see far deeper into space than technology alone would normally allow. This happens through a phenomenon known as gravitational lensing, a remarkable effect predicted by Albert Einstein's theory of general relativity. According to this theory, gravity does more than simply pull objects together. Massive objects, such as galaxies and galaxy clusters, actually bend the fabric of space itself. When light from a distant galaxy travels through this curved region of space, its path is bent as well. Instead of moving in a perfectly straight line, the light curves around the massive object before continuing toward Earth. To an observer with a telescope, the background galaxy can appear distorted, stretched, or even multiplied into several images. Sometimes the bending creates long arcs of light across the sky. In rare cases, the light forms an almost perfect circle known as an Einstein ring. At first, these shapes might look like strange visual accidents, but they are actually powerful tools that astronomers use to study the universe. By carefully measuring how the light is bent, scientists can determine how much mass is present in the lensing object. What makes this especially fascinating is that much of that mass may not be visible at all. A large portion of the universe appears to be made of dark matter, a mysterious substance that does not emit or reflect light. Even though we cannot see dark matter directly, its gravity still bends light. Gravitational lensing, therefore, allows astronomers to map the distribution of this invisible material. But lensing does something else as well. In some situations, the bending of light also magnifies the distant galaxy behind the lens. The effect can make a very faint and distant galaxy appear brighter and larger than it normally would. In this way, gravity acts like a giant cosmic magnifying glass. This magnification allows astronomers to observe galaxies that would otherwise be far too faint to detect. Some of the most distant galaxies ever studied were discovered thanks to gravitational lensing created by massive galaxy clusters in the foreground. When scientists examine these magnified galaxies, they are often seeing systems that formed extremely early in the history of the universe. These galaxies may contain only a few billion stars, compared with the hundreds of billions found in large modern galaxies. Yet they provide valuable clues about how the first galaxies assembled from clouds of gas and dark matter. In many cases, these early galaxies appear irregular and clumpy. Their shapes suggest that they are still in the process of forming, with star-forming regions scattered unevenly throughout their structures. Some contain intense bursts of star formation, while others appear quieter and more stable. The study of these galaxies helps astronomers understand how the first structures in the universe gradually grew larger and more complex over time. Each observation adds another piece to the puzzle of cosmic evolution. And as telescopes continue to improve, revealing fainter and distant galaxies, the picture becomes even richer. We begin to see not only how galaxies formed, but also how they changed as the universe aged and settled into the vast cosmic landscape we observe today.
When astronomers observe distant galaxies closely, one of the first clues they study is color. At first glance, the color of a galaxy may seem like a simple visual detail, but in reality, it reveals an enormous amount about what is happening inside that system. The light from a galaxy is the combined glow of billions of stars, and the types of stars present can change the color of that light in subtle but meaningful ways. Young stars are usually very hot and energetic. They burn their fuel quickly and shine with a bright bluish light. When a galaxy is actively forming new stars, large numbers of these hot blue stars dominate its appearance. As a result, the galaxy tends to glow with cooler blue or white tones, signaling that star formation is happening rapidly. But stars do not live forever. The most massive and brightest stars use up their fuel in only a few million years, which is a very short time compared with the age of the universe. Once these stars die, the remaining population is made up mostly of smaller, longer-lived stars that shine with softer, redder light. Because of this, galaxies that have slowed down or stopped forming new stars often appear redder. Their bright blue stars have already faded away, leaving older generations of stars to provide most of the light we see. Astronomers sometimes describe these systems as quiet or resting galaxies because their intense periods of star formation have already passed. To study these differences carefully, scientists observe galaxies through multiple filters that isolate different wavelengths of light. By comparing how bright a galaxy appears in each wavelength, astronomers can estimate the mixture of stars inside it. This technique allows them to determine whether the galaxy is still building new stars or whether it has largely settled into a slower stage of evolution. Dust inside galaxies also plays an important role in shaping what we see. Cosmic dust is made of extremely small grains, often no larger than particles of smoke. Even though these grains are tiny, they are very effective at absorbing and scattering visible light. When large amounts of dust surround star-forming regions, the bright young stars inside may become partially hidden. The galaxy can appear dimmer or redder than it truly is because the dust blocks some of the blue light from escaping. In these cases, astronomers turn to infrared observations once again. Infrared light can pass through dust much easier than visible light. Telescopes that detect infrared radiation are therefore able to reveal star-forming regions that would otherwise remain concealed behind dusty clouds. When scientists combine visible and infrared observations, they gain a more complete understanding of how galaxies are building their stars. By examining color, dust, and star formation together, astronomers can piece together the life stories of galaxies across cosmic time. Some galaxies are still busy growing and creating new stars at remarkable rates. Others have entered quieter phases where star formation has slowed dramatically. These patterns reveal that galaxies evolve in different ways depending on their environments, their histories of collisions and mergers, and the supply of gas available to form new stars. And as we continue exploring deeper into the distant universe, we begin to notice that long ago there was a time when star formation across the cosmos was far more intense than it is today.
As astronomers continued mapping galaxies across vast distances, they began to notice a surprising pattern. When they looked far enough back in time, they found that the universe once experienced an era of extraordinary activity. During this period, galaxies across the cosmos were forming stars at a much faster rate than they do today. Scientists sometimes refer to this era as cosmic noon, a time when the universe was in the middle of its most energetic phase of star creation. Billions of years ago, galaxies contained enormous reservoirs of cold hydrogen gas. This gas acted as the raw material for star formation. When gravity pulled these clouds together, the gas would collapse into dense regions where new stars could ignite. Because so much gas was available, galaxies could create stars at remarkable speeds, sometimes producing hundreds of new stars every year. In comparison, the Milky Way today forms only a few new stars annually. This difference highlights just how active the earlier universe was. Many galaxies during cosmic noon glowed brightly with young stars, and their structures were often shaped by powerful bursts of star formation triggered by interactions and mergers. Collisions between galaxies played an important role during this time. When two galaxies approached each other, their immense gravitational forces stirred their gas clouds and compressed them. This compression often caused sudden waves of star formation, lighting up entire regions of the galaxies with clusters of newly born stars. These bursts of activity could dramatically change a galaxy's appearance. Bright blue star clusters would appear across its structure, and powerful winds from young stars could push gas outward into space. Some galaxies briefly became what astronomers call starburst galaxies. systems that produce stars at extremely high rates for relatively short periods of time. But these intense phases could not last forever. As stars formed in large numbers, they gradually consumed the available gas that fueled the process. At the same time, energetic events such as supernova explosions and radiation from massive stars heated the surrounding gas. Heated gas becomes more difficult to compress, making it harder for new stars to form. Over billions of years, these effects slowly reduced the overall rate of star formation across the universe. Galaxies began transitioning from energetic youth into calmer maturity. Many systems that once formed stars rapidly eventually used up much of their star-forming fuel. Another powerful influence came from the centers of galaxies themselves. Many galaxies contain supermassive black holes at their cores. When these black holes actively pull in surrounding gas, they can release enormous amounts of energy into their surroundings. This energy can heat nearby gas or even push it away from the galaxy entirely. When this happens, the supply of gas needed for star formation becomes limited. Without fresh gas collapsing into dense regions, the creation of new stars slows or stops altogether. Astronomers describe these galaxies as quenched galaxies, systems where star formation has largely ceased. Yet even when star formation ends, galaxies do not disappear. Their existing stars continue shining quietly for billions of years, gradually aging and cooling over time. These calmer places become mostly filled with older stars whose soft reddish light tells the story of a once far more energetic past.
Even though many galaxies eventually settle into quieter stages, the universe still contains remarkable variety in how galaxies appear and behave. Some display elegant spiral arms winding outward like gentle cosmic pinwheels, while others appear smooth and rounded with little visible structure. Still others look chaotic and irregular, as though they are still trying to decide what shape they want to become. One of the most familiar galaxy shapes is the spiral galaxy. In these systems, stars, gas, and dust rotate together in a flattened disk. Within that disk, graceful spiral arms stretch outward from the center, glowing with clusters of young stars and bright clouds of gas. Our own Milky Way belongs to this category, though we can only imagine its full appearance from within. For a long time, astronomers believed that spiral galaxies required billions of years to develop their organized structures. The assumption seemed reasonable. In the early universe, galaxies were smaller, more crowded, and frequently disturbed by interactions with neighbors. Under those conditions, it seemed unlikely that delicate spiral patterns could survive. Yet modern observations have revealed something surprising. Some distant galaxies, seen when the universe was much younger, already display clear spiral structures. These discoveries suggest that certain galaxies managed to settle into rotating disks much earlier than scientists once expected. To form a spiral galaxy, gas within the galaxy must gradually flatten into a rotating disk. Gravity pulls matter inward, while the motion of the gas spreads it outward into a stable, rotating structure. Once that disk forms, waves of density can travel through it. These waves act like gentle traffic patterns, temporarily crowding stars and gas into spiral shapes as they move through the disk. Where these density waves pass, gas clouds can become compressed, triggering the birth of new stars.
This is why spiral arms often glow with bright blue star clusters. The arms are not fixed structures, but regions where star formation happens more actively as the waves move through the disk. Seeing spiral galaxies in the distant universe raises intriguing questions. How were these galaxies able to maintain such organized structures in an era when interactions and mergers were more common? Did they form in quieter regions of space, away from frequent disturbances? Or did their disks reform quickly after earlier collisions? Astronomers continue to investigate these questions by studying the motion of stars and gas within distant spiral galaxies. By measuring how fast the material inside them rotates, scientists can learn how mass is distributed throughout the galaxy. These measurements often reveal that large amounts of unseen mass must be present to hold the galaxies together. That unseen mass is believed to be dark matter, which surrounds galaxies in enormous halos extending far beyond their visible stars. The gravitational influence of these halos helps stabilize rotating disks, allowing spiral structures to form and persist. In this way, spiral galaxies reveal the hidden architecture of the universe. Their graceful shapes are guided not only by the stars we see, but also by the invisible matter that surrounds them. And while some galaxies settle into these elegant patterns, others remain far more chaotic, filled with bright clumps of star formation that hint at a much more turbulent stage of growth.
When astronomers look deep into the distant universe, many galaxies do not show the smooth spiral shapes we often imagine. Instead, they appear uneven and clumpy, with bright patches scattered across their surfaces like islands of light. At first glance, these galaxies can look disorganized, almost unfinished. Yet these clumps are not random imperfections. They are signs of intense activity happening within young galaxies. In the early universe, galaxies contained much larger amounts of gas than most galaxies do today. This gas was the primary fuel for star formation. Under the pull of gravity, large regions of gas could become unstable and collapse into massive knots. Each of these knots could form enormous clusters of new stars, far larger than the typical star-forming regions seen in nearby galaxies. These giant star-forming clumps often contained millions of stars and produced brilliant light that made them stand out clearly in telescope images. Some of these regions were so large that they dominated the entire appearance of the galaxy, giving it a patchy and irregular structure. Over time, these clumps did not remain fixed in place. The gravitational forces inside the galaxy caused them to slowly move and interact with one another. Some clumps merged together, while others gradually migrated toward the central regions of the galaxy. As this happened, the galaxy's structure slowly evolved. Astronomers believe that this process may have played an important role in building the dense central bulges seen in many galaxies today. As star-forming clumps drifted inward and combined, they may have helped create the concentrated cores that later became stable centers of mature galaxies. Observing these clumpy galaxies, therefore, provides valuable insight into how galaxies assembled their structures during their early stages. Rather than forming all at once, galaxies appear to have grown through a series of dynamic processes where gas collapsed, stars ignited, and structures gradually emerged over time. Another surprising discovery about some distant galaxies is how compact they can be. In certain cases, astronomers have found galaxies that contain enormous numbers of stars packed into very small regions of space. These systems may hold as much mass as large modern galaxies, yet their visible sizes are only a fraction as wide. Inside these compact galaxies, stars move at extremely high speeds as they orbit within the strong gravitational pull of the system. The density of stars can be far greater than what we observe in many galaxies today. These systems represent a stage of galaxy evolution that may have occurred before galaxies expanded into the larger structures we see in the present universe. Scientists think that some of these compact galaxies may eventually grow through mergers and gradual accumulation of additional material. Over billions of years, these processes may allow them to expand and transform into the massive elliptical galaxies observed today. By studying clumpy and compact galaxies together, astronomers gain a clearer picture of the many pathways galaxies can take as they evolve. Some grow through calm, steady star formation, while others pass through intense and crowded phases before settling into the shapes we recognize today.
While some galaxies grow into elegant spirals and others pass through clumpy, energetic stages, another group of galaxies follows a very different path of evolution. These are known as elliptical galaxies. At first glance, they appear calm and simple, glowing as smooth oval shapes, without the dramatic arms or bright patches seen in many other galaxies. But this peaceful appearance hides a surprisingly dramatic past. Elliptical galaxies are often the result of repeated collisions and mergers between smaller galaxies over long stretches of cosmic time. When two spiral galaxies slowly move toward one another, their gravitational pull begins to distort their shapes. Long tidal tails of stars and gas can stretch outward as the galaxies interact, and their internal motions become increasingly chaotic. Eventually, the galaxies merge completely. During this process, the orderly rotation that once formed spiral arms becomes disrupted. Instead of moving together in a flat, rotating disk, the stars begin orbiting in many different directions. Over time, this mixing produces a rounded, three-dimensional structure where stars move through the galaxy in complex paths. The result is the smooth, featureless glow that we recognize as an elliptical galaxy. Inside these galaxies, star formation is usually much slower than in spiral systems. Most elliptical galaxies contain older stars that formed earlier in the universe's history. Without large amounts of cold gas remaining, there is little material available to create new generations of stars. Because of this, elliptical galaxies often shine with a warmer reddish light produced by their aging stellar populations. Their calm appearance can give the impression that they have always been quiet systems, but in reality, they are often the end products of many earlier interactions. Astronomers sometimes find subtle traces of those past encounters. Very faint shells, ripples, or arcs of stars may surround some elliptical galaxies, like gentle wrinkles in the light. These features are leftovers from previous mergers, slowly fading as the galaxy settles into a stable shape. Despite their peaceful look, elliptical galaxies can be enormous. Some of the largest galaxies in the universe belong to this category, containing trillions of stars. Many of these giants sit at the centers of massive galaxy clusters, where countless smaller galaxies orbit around them.
Over billions of years, these central galaxies can grow by gradually absorbing nearby companions. Each new merger adds stars and mass, slowly increasing the galaxy's size. Yet, galaxies do not only grow by consuming large neighbors. Sometimes, the smallest galaxies also play an important role in shaping cosmic history. In fact, some of the most valuable clues about how galaxies formed come from studying systems that are much smaller than the Milky Way. These are known as dwarf galaxies. Though they contain far fewer stars than giant galaxies, dwarf galaxies are incredibly important for understanding how structure developed in the universe. In many ways, these small galaxies act like cosmic fossils, preserving information about the earliest stages of galaxy formation and revealing how the universe gradually assembled its vast and complex structures.
Dwarf galaxies may be small compared with giants like the Milky Way, but they play a surprisingly important role in the story of the universe. Many of these galaxies contain only a few billion stars, and some hold even fewer. In comparison, the Milky Way contains hundreds of billions of stars spread across its vast spiral disk. Because dwarf galaxies are so small, their gravity is much weaker than that of larger galaxies. This difference makes them more sensitive to changes in their environments. Processes that a massive galaxy might barely notice can dramatically reshape a dwarf galaxy over time. For example, powerful stellar explosions called supernovae can have a stronger influence inside these smaller systems. When massive stars end their lives in supernova explosions, they release enormous amounts of energy. In a large galaxy, this energy spreads through vast clouds of gas without greatly altering the overall structure. But in a dwarf galaxy, the same explosions can push gas outward more easily. When gas is blown out of the galaxy, the supply of material needed to create new stars decreases. As a result, star formation in dwarf galaxies often happens in bursts. A period of intense star formation may occur, followed by a quieter phase while the galaxy slowly gathers more gas again. Because these galaxies experience fewer mergers and disturbances than larger systems, some dwarf galaxies preserve relatively simple histories. Their stars can retain chemical signatures that reveal the conditions present when they first formed. By studying the elements inside these stars, astronomers can learn about the earliest generations of star formation in the universe. Dwarf galaxies may also represent the building blocks from which larger galaxies grew. In the early universe, many small galaxies formed first. Over billions of years, gravity gradually pulled them together, merging them into larger systems. This process of gradual assembly continues even today. Large galaxies can still capture nearby dwarf galaxies through gravitational attraction. When this happens, the smaller galaxy may begin orbiting its larger neighbor while slowly being stretched apart by tidal forces. As the dwarf galaxy is pulled apart, its stars are stripped away and spread along long streams that wrap around the larger galaxy. These streams can stretch for enormous distances across space, forming faint arcs of stars that trace the path of the dwarf galaxy's former orbit. Astronomers often search for these stellar streams in deep images of the sky. They appear as delicate rivers of light flowing through the outer regions of large galaxies. Each stream represents the remnants of a smaller galaxy that was gradually torn apart by gravity. These streams are more than beautiful features. They provide valuable clues about the invisible structure surrounding galaxies. The paths followed by the stars respond to the gravitational pull of dark matter halos that extend far beyond the visible stars of a galaxy. By mapping the shapes and motions of these streams, astronomers can better understand how dark matter is distributed around galaxies and how galaxies continue to grow by slowly gathering smaller companions across cosmic time.
As astronomers continue mapping the faint stellar streams left behind by disrupted dwarf galaxies, they gain a deeper understanding of how galaxies grow over time. These delicate rivers of stars act almost like footprints, marking the paths that smaller galaxies once followed as they orbited larger systems before eventually being pulled apart by gravity. Each stream is a quiet reminder that galaxies are not isolated islands drifting alone through space. Instead, they are constantly interacting with their surroundings. Even today, the Milky Way itself is slowly absorbing smaller neighboring galaxies. Several faint stellar streams have already been discovered stretching across our own galaxy's halo, revealing past encounters that unfolded over billions of years. These discoveries show that galaxy growth is often a gradual and continuous process. Rather than forming all at once, galaxies build themselves step by step by collecting smaller companions and merging with them over long periods of time. But while gravity pulls galaxies together, other forces can shape them from within. One of the most powerful influences inside many galaxies comes from an object that is almost impossible to see directly: a supermassive black hole. At the center of nearly every large galaxy lies a black hole with a mass millions or even billions times greater than that of our Sun. These black holes are surrounded by swirling disks of gas and dust that slowly spiral inward under the pull of gravity. As this material falls toward the black hole, it becomes extremely hot and begins to shine with tremendous brightness. In some cases, the energy released by this infalling material can outshine all the stars in the galaxy combined. When this happens, astronomers refer to the galaxy's core as an active galactic nucleus, or AGN. One of the most dramatic examples of this phenomenon is known as a quasar. Quasars are among the brightest objects in the universe. Their intense light can travel across billions of light years, allowing astronomers to observe them even from the very distant past. Despite their incredible brightness, the glowing region around a quasar is actually quite small compared with the size of the entire galaxy. This brightness comes from the enormous energy released as matter accelerates and heats up while spiraling toward the black hole. Friction within the swirling disk raises temperatures to extreme levels, producing radiation across many wavelengths of light. Sometimes these active black holes also launch powerful jets of energy and particles outward from the galaxy's center. These jets can extend for thousands or even millions of light years into intergalactic space, shaping the surrounding environment in dramatic ways. The influence of a supermassive black hole does not stop at producing light and jets. The energy released near the galaxy's core can also heat or push away nearby gas. When gas is removed or heated too much, it becomes harder for the galaxy to form new stars. In this way, black holes may play a crucial role in regulating the growth of galaxies. They help determine when star formation continues and when a galaxy begins to settle into a quieter stage of its life.
As we look deeper into the universe, we begin to see how these powerful engines shaped many of the galaxies we observe today.
As astronomers studied more galaxies across different distances, another fascinating pattern slowly became clear. Not all galaxies continue forming stars forever. Some galaxies appear vibrant and active, filled with glowing blue regions where new stars are constantly being born. Others look quieter and older, shining with a softer reddish light that suggests their most active years are long behind them. This transition from active star formation to a quieter state is known as galactic quenching. A quenched galaxy is not empty or lifeless. It still contains billions of stars that continue to shine for enormous spans of time. What has changed is the galaxy's ability to create new stars. For stars to form, a galaxy needs large reservoirs of cold gas. This gas must be able to collapse under gravity into dense clouds where nuclear fusion can ignite. But several processes can interrupt this cycle and prevent new stars from forming. One common cause is the gradual consumption of gas. During periods of intense star formation, galaxies can use up much of their available gas over time. As the fuel supply decreases, the rate of star birth naturally slows down. Another possibility involves heating the gas so that it cannot collapse easily. Energy released by supernova explosions or powerful radiation from massive stars can warm surrounding gas clouds. When gas becomes too hot, it spreads out rather than condensing into star-forming regions. Supermassive black holes may also contribute to this process. As material falls toward a black hole at the center of a galaxy, enormous amounts of energy can be released. This energy can push gas away from the central regions or heat it enough to prevent further star formation. Environmental effects can also influence galaxies. In dense galaxy clusters, large numbers of galaxies move through hot gas that fills the space between them. As a galaxy travels through this environment, some of its own gas may be stripped away by pressure from the surrounding medium. Without that gas, the galaxy loses its ability to produce new stars. When star formation stops, the galaxy gradually changes in appearance. The bright blue stars that once dominated its light fade relatively quickly because they burn their fuel so rapidly. What remains are older, longer-lived stars that emit softer, redder light. Over time, the galaxy becomes quieter and more stable. Its stars continue orbiting through space, but the dramatic bursts of new star formation have ended. Astronomers often describe these systems as red and dead, though the phrase can be a bit misleading. Even in these calmest forms, galaxies continue carrying the memory of everything that shaped them across billions of years. As galaxies pass through different stages of activity and quietness, astronomers often turn their attention to the environments where galaxies live. Just as cities on Earth grow differently depending on their surroundings, galaxies can also evolve in different ways depending on whether they exist alone, in small groups, or inside enormous clusters filled with hundreds or even thousands of galaxies. Galaxy clusters are some of the largest gravitational structures in the universe. Within these vast regions, galaxies move through space while bound together by the combined pull of their gravity and the invisible presence of dark matter. The spaces between the galaxies are not completely empty either. They are filled with extremely hot gas that glows faintly in X-ray light. Inside these crowded environments, galaxies interact with one another more frequently. Close encounters can distort their shapes, trigger bursts of star formation, or even lead to complete mergers where two galaxies slowly combine into a single, larger system. But clusters also contain powerful forces that can strip galaxies of their gas. As a galaxy travels through the hot gas that fills a cluster, pressure from that environment can push against the galaxy's own gas clouds. This process is sometimes called ram pressure stripping. Gradually, the galaxy may lose the gas that would normally be used to create new stars. Without fresh gas, star formation begins to slow. Over time, many galaxies inside clusters become redder and quieter compared with galaxies that live in more isolated regions of space. Astronomers studying clusters have noticed that elliptical galaxies are especially common in these dense environments. Because collisions and interactions occur more frequently in clusters, spiral galaxies can be disrupted and transformed through repeated mergers. The result is a population of galaxies that appear smoother and more rounded. In contrast, galaxies that live in quieter regions of space often maintain their spiral shapes for longer periods of time. Without constant disturbances from neighbors, their rotating disks remain stable, allowing spiral arms to continue forming new stars over billions of years. By comparing galaxies across these different environments, scientists gain a clearer understanding of how surroundings influence galaxy evolution. A galaxy's future is not determined only by its internal structure. Its neighborhood also plays an important role in shaping what it will eventually become. These environmental influences extend across enormous cosmic distances. Entire clusters can span millions of light years, containing hundreds of galaxies moving within vast halos of dark matter. Yet even these immense clusters are not isolated from the rest of the universe. They connect to one another along the giant filaments of the cosmic web. Along these filaments, galaxies and gas slowly flow toward the densest regions, where clusters continue growing over time. This means that galaxies are part of an even larger network of structure stretching across the universe. From small dwarf galaxies to enormous clusters, everything is connected through the steady pull of gravity. And as astronomers observe galaxies at greater distances, they are not only seeing how individual galaxies evolve, but also how this entire cosmic network gradually assembled itself across billions of years.
When astronomers look deeper into the distant universe, they began to notice that galaxies were not always as organized as many of the ones we see nearby today. In the earliest epochs, galaxies often appeared smaller, messier, and far more chaotic. Their stars and gas had not yet settled into the graceful spiral arms or smooth elliptical shapes that later became common. Instead, many early galaxies looked irregular and uneven, filled with bright patches of star formation scattered throughout their structures. These clumpy appearances reflect a time when galaxies were still actively gathering material from the surrounding universe. During those early ages, vast streams of gas flowed along the filaments of the cosmic web toward growing galaxies. This gas provided the fuel needed for new stars to ignite. As the gas entered a galaxy's gravitational influence, it could form turbulent clouds that collapsed into intense star-forming regions. These regions often produced enormous clusters of stars that lit up their surroundings. The brightness of these clusters made them stand out clearly in telescope images, giving young galaxies their patchy and irregular appearance. Over time, gravity continued shaping these galaxies.
Stars and gas gradually moved into more organized patterns as the galaxies rotated and interacted with nearby systems. Some galaxies experienced repeated mergers that stirred their structures, while others slowly settled into rotating disks. Astronomers studying distant galaxies sometimes compare these early systems to construction sites where the work of building galaxies was still underway. Gas clouds were collapsing, stars were forming in large groups, and gravity was constantly reshaping the growing structures. Another interesting discovery about early galaxies is how quickly some of them managed to accumulate mass. Observations show that even when the universe was only a few billion years old, some galaxies had already grown quite massive. These systems likely formed through a combination of rapid star formation and repeated mergers with smaller galaxies. Each merger brought additional stars and gas, gradually increasing the galaxy's size and mass. At the same time, many galaxies were surrounded by enormous halos of dark matter. These halos provided the gravitational framework that allowed galaxies to gather material from the surrounding universe. Although dark matter cannot be seen directly, its presence is essential for explaining how galaxies formed and evolved. Without the additional gravitational pull of dark matter, the visible matter in galaxies would not have been able to clump together quickly enough to form the structures we observe today. As scientists examine galaxies across different distances, they can see these stages of growth unfolding across cosmic time. Nearby galaxies often appear more settled and mature, while distant galaxies reveal earlier phases of assembly and transformation. This ability to see different eras of galaxy evolution within the same universe is one of the most remarkable aspects of astronomy. Each distant galaxy acts like a window into a different moment in time, and the farther we look, the closer we come to seeing the very first galaxies that formed after the universe emerged from its earliest darkness.
When astronomers push their observations even farther into space, they begin approaching a time when the very first galaxies were just beginning to appear. This was an era when the universe itself was still young, only a few 100 million years old. Before that time, the cosmos had gone through a long period, often called the Cosmic Dark Ages. During the Dark Ages, the universe contained vast clouds of hydrogen and helium gas left over from the earliest moments after the Big Bang. Stars had not yet formed, so there were no sources of light shining across space. The universe was filled with darkness, slowly evolving as gravity began gathering matter into denser regions. Eventually, those regions of gas grew dense enough for the first stars to ignite. These early stars were very different from most stars we see today. Because the universe contained only the simplest elements at that time, these stars were often extremely massive and burned their fuel quickly. When the first stars began shining, they transformed the universe in profound ways. Their intense radiation started to ionize the surrounding hydrogen gas, gradually clearing the fog that filled space. This period is known as the epoch of re-ionization, when the light from early stars and galaxies slowly illuminated the cosmos. Within these first galaxies, star formation could be intense and energetic. Clouds of gas collapsed rapidly, forming clusters of massive stars that lived short but brilliant lives. Many of these stars ended in powerful supernova explosions, scattering heavier elements into space. These elements became the building blocks for future generations of stars and planets. Over time, each new generation of stars enriched the surrounding gas with more complex atoms.
This gradual enrichment allowed later stars to form with a wider variety of elements, eventually leading to the chemical diversity we see in the universe today. Detecting these early galaxies is extremely challenging. Their light has traveled for more than 13 billion years before reaching us. During that journey, the expansion of the universe stretched their light into longer wavelengths, shifting much of it into the infrared region of the spectrum. Modern space telescopes designed to detect infrared light have allowed astronomers to glimpse some of these ancient galaxies. Even though they appear incredibly faint, their discovery provides valuable information about how quickly the first structures formed after the universe's beginning. Some of these early galaxies already contain millions or even billions of stars, suggesting that galaxy formation may have started sooner than scientists once expected. These discoveries continue to refine our understanding of how the young universe evolved. As researchers study these distant systems, they are essentially observing the earliest chapters in the history of galaxies. Each faint glow represents a time when the universe was still learning how to build the vast structures we see today. And as our telescopes grow more powerful, we move closer to witnessing the moment when the first galaxies emerged from the darkness and began lighting up the universe for the very first time.
As astronomers continued exploring the distant universe, they began noticing that galaxies were not only forming earlier than expected, but they were also changing rapidly during those early billions of years. Many young galaxies appeared to be growing at remarkable speeds, gathering gas and merging with nearby systems as gravity steadily pulled matter together across cosmic distances. In the early universe, galaxies lived much closer to one another than they do today. Space itself was smaller because cosmic expansion had not yet stretched the distances between structures as dramatically as it has over billions of years. Because galaxies were closer together, gravitational encounters were far more common. When two galaxies drifted near each other, their mutual gravity began to tug on their stars and gas. Long tidal streams of material could stretch outward as the galaxies interacted, sometimes forming delicate bridges of stars connecting the two systems. These encounters could last for millions of years before the galaxies finally merged into a single, larger structure. During these mergers, something remarkable often happened inside the galaxies. As their gas clouds collided and compressed, they triggered enormous waves of star formation. Entire regions of the galaxies could suddenly light up with clusters of newly born stars. Astronomers call these events starbursts. During a starburst, a galaxy may form stars dozens or even hundreds of times faster than usual. Bright blue star clusters can appear across the merging galaxies, illuminating their structures with intense energy. However, these dramatic periods of star formation do not last forever. As gas is rapidly converted into stars, the available fuel begins to diminish. Eventually, the galaxy returns to a slower pace of star creation once its most intense starburst phase has passed. Mergers also play a crucial role in shaping the long-term structure of galaxies. When two spiral galaxies merge, the orderly rotation that once defined their disks can be disrupted. Stars begin moving along new paths, and the combined system may eventually settle into a rounded elliptical galaxy. In this way, the repeated merging of galaxies acts as a powerful engine of transformation across cosmic time. Small galaxies combine to form larger ones, while their internal structures evolve through these interactions.
Astronomers studying distant galaxies often see clear evidence of these processes. Some galaxies appear stretched or distorted, showing long tails of stars pulled outward by tidal forces. Others display multiple bright cores, indicating that two galaxies are still in the process of merging. These observations reveal that the universe has always been dynamic and constantly changing. Even galaxies that appear calm and stable today may have experienced dramatic encounters billions of years ago. And as we continue our quiet journey deeper into the universe, we begin to see how these countless interactions gradually shaped the vast population of galaxies that now fill the cosmos.
While galaxy mergers and starbursts help explain how galaxies grow larger, another fascinating detail begins to appear when astronomers study the faintest and most distant systems. Many galaxies that look like tiny smudges in telescope images actually contain enormous numbers of stars. Even though they appear small and dim from Earth, their true scale can be astonishing. The reason these galaxies appear faint is not because they lack stars, but because of the immense distances separating them from us. Light spreads out as it travels through space. By the time the glow from a distant galaxy reaches Earth, it has expanded across an enormous region of the universe. What remains is only a very faint signal that telescopes must carefully collect. Astronomers often observe these faint galaxies using long exposure times. Instead of capturing an image in a single moment, telescopes gather light slowly over hours or even days. Each tiny photon adds to the picture, gradually revealing structures that would otherwise remain invisible. When these deep observations are complete, the results can be extraordinary. A region of sky that once appeared completely empty becomes filled with hundreds or thousands of distant galaxies. Each faint speck represents a massive system containing billions of stars. By analyzing the brightness of these galaxies, astronomers can estimate how many stars they contain. Even when a galaxy appears as only a tiny blur of light, careful measurements of its brightness and color allow scientists to determine its approximate mass and structure. Sometimes these faint galaxies surprise researchers by containing far more stars than expected. A galaxy that appears barely visible in an image may actually host vast numbers of stars packed into its distant structure. The dimness we observe is simply the result of the incredible distance the light has traveled. Studying these faint galaxies also reveal important details about how galaxies evolved over time. Some appear small and compact, suggesting they represent earlier stages of galaxy growth. Others already show signs of complex structures, even though their light began traveling billions of years ago. These observations remind us that the universe is far more crowded than our eyes alone can reveal. The night sky may appear calm and mostly empty, but powerful telescopes reveal an immense population of galaxies stretching across space in every direction. Each of those galaxies holds its own history of star formation, mergers, and transformation. Together, they form the vast cosmic landscape that has developed over billions of years. As we continue exploring deeper into space, we also begin to notice that some galaxies shine with unusual brightness. Their centers glow intensely, sometimes outshining all the stars surrounding them. These brilliant cores hint at the presence of something extraordinary hidden at the heart of the galaxy. In many cases, that extraordinary source of energy comes from a powerful engine, fueled not by nuclear fusion like ordinary stars, but by the immense gravitational pull of a supermassive black hole. At the center of many galaxies lies one of the most mysterious objects in the universe, a supermassive black hole. These extraordinary objects contain millions or even billions times the mass of our Sun. Yet they occupy regions of space far smaller than the galaxies that surround them. For a long time, astronomers suspected that black holes might exist in galaxy centers, but only in recent decades has strong evidence confirmed just how common they are. Despite their name, black holes are not always completely dark. The black hole itself does not emit light, but the material falling toward it can become incredibly bright. Gas and dust drawn toward the black hole begin spiraling inward, forming a rotating structure known as an accretion disk. Inside this disk, the gas moves at tremendous speeds. Friction and gravitational forces heat the material to extreme temperatures, causing it to glow with intense radiation. In some galaxies, this process releases more energy than all the stars in the galaxy combined. When this happens, the galaxy's center becomes what astronomers call an active galactic nucleus. These energetic cores can shine across enormous distances, making them visible even when the rest of the galaxy is faint. Some of the brightest examples are known as quasars. Quasars are among the most luminous objects ever observed in the universe. Their brilliant light can travel billions of light years through space before reaching Earth. When astronomers observe a quasar, they are often seeing the glow from a galaxy's center at a time when the universe was much younger. Even though quasars appear incredibly bright, the region producing that light is relatively small compared with the size of the host galaxy. The energy comes from matter accelerating and heating as it spirals toward the black hole, converting gravitational energy into radiation with remarkable efficiency. In some cases, the activity near the black hole also launches powerful jets of particles outward from the galaxy's center. These jets can travel vast distances into intergalactic space, sometimes extending far beyond the visible boundaries of the galaxy itself. The presence of an active black hole can influence the entire galaxy. Energy released near the center can heat surrounding gas or push it outward into space. When this happens, the gas needed to form new stars may become unavailable, slowing down the galaxy's star formation. Because of this, astronomers believe supermassive black holes may play an important role in controlling how galaxies evolve. The relationship between galaxies and their central black holes appears to be closely connected, suggesting that both grow and change together over time. When we observe distant galaxies with bright active cores, we are witnessing moments when these powerful engines were shaping their host galaxies. And as our journey continues deeper into the universe, we begin to notice that not all galaxies remain active forever. Some gradually quiet down, entering calmer stages where their brilliant central activity slowly fades away.
As galaxies age and evolve, many of them eventually transition into calmer and more stable systems. The brilliant activity that once filled them with rapid star formation or powerful black hole emissions gradually slows down. These quieter galaxies still contain enormous numbers of stars, but the processes that once fueled their growth become less intense over time. Astronomers often describe this stage as a galaxy's mature phase. The galaxy continues to shine, but most of its stars are older and cooler.
Without large supplies of fresh gas collapsing into new star-forming regions, the bright blue stars that once dominated its light slowly disappear. What remains are long-lived stars that burn their fuel gently for billions of years. These stars tend to glow with warmer, reddish tones, giving many older galaxies their soft, calm appearance. This change in color is one of the most important clues astronomers use when studying galaxy evolution. By examining how blue or red a galaxy appears, scientists can estimate whether it is still actively forming stars or whether it has entered a quieter stage of life. But galaxies do not exist in isolation. Even when their internal activity slows, their surroundings continue influencing them. Some galaxies drift through regions of space where interactions with neighbors still occur. Others move within enormous galaxy clusters where gravitational forces shape their long-term evolution. Inside these clusters, galaxies orbit within huge halos of dark matter while surrounded by extremely hot gas filling the space between them. As galaxies travel through this environment, some of their own gas can be stripped away by pressure from the surrounding medium. Without that gas, star formation becomes even more difficult. Over time, galaxies inside clusters often become dominated by older stars and gradually lose the bright blue glow associated with young stellar populations. Yet, even in these quieter galaxies, the story of their earlier lives remains written in their structures. Astronomers sometimes detect faint shells, ripples, or extended halos of stars surrounding older galaxies. These subtle features are the leftovers of past mergers and interactions that shaped the galaxy long ago. By studying these delicate patterns, scientists can reconstruct events that happened billions of years earlier. A faint arc of stars might represent the remnants of a smaller galaxy that was absorbed in the distant past. A slightly distorted halo could reveal an ancient gravitational encounter. In this way, galaxies act like cosmic archives. Their shapes, colors, and star populations preserve information about the events that formed them. When we observe distant galaxies across different epochs of time, we begin to see how these stories unfold. Some galaxies are still energetic and forming stars rapidly, while others have already reached quieter stages. Together, they reveal the long journey galaxies take from chaotic beginnings toward calmer, more stable forms. And as our view stretches even farther into the depths of space, we discover that galaxies themselves are only one part of an even larger cosmic structure, connecting everything across the universe. As astronomers continued mapping galaxies across greater and greater distances, they began to realize that galaxies themselves are only part of a much larger structure. When scientists chart the positions of millions of galaxies across the sky, a vast pattern slowly emerges. Galaxies are not scattered randomly throughout space. Instead, they trace enormous filaments that stretch across the universe like glowing threads in a gigantic web. This structure is known as the cosmic web. It is one of the largest patterns in the universe, spanning hundreds of millions of light years. Along these filaments, galaxies gather in clusters and groups where gravity has drawn matter together over billions of years. Between the filaments lie enormous regions called cosmic voids. These voids contain very few galaxies. Some of them stretch across tens or even hundreds of millions of light years, creating vast empty spaces between the brighter strands of the cosmic web. If we could step far outside the universe and look back at this structure from a great distance, it might resemble a glowing network of filaments with large dark bubbles between them. The formation of this enormous structure began very early in the universe's history. Shortly after the universe began expanding, tiny differences in density were scattered throughout space. Some regions contained slightly more matter than others. Over immense spans of time, gravity slowly amplified those small differences. Regions that were a little denser began pulling in more material from their surroundings. Gas and dark matter flowed toward these areas, gradually forming long filaments where galaxies could grow. The densest intersections of these filaments eventually became galaxy clusters, where hundreds or even thousands of galaxies gather together. Dark matter plays a crucial role in shaping this cosmic web. Although it cannot be seen directly, dark matter provides most of the gravitational framework that allows galaxies and clusters to form. Invisible halos of dark matter surround galaxies and extend far beyond the stars we observe. These halos connect to the larger network of dark matter filaments stretching across the universe. Gas follows the gravitational pull of these filaments, flowing toward growing galaxies and fueling the formation of new stars. As galaxies collect material from these cosmic streams, they gradually grow in mass. Some galaxies experience steady flows of gas that allow them to continue forming stars for billions of years. Others may merge with neighboring galaxies along the filaments, building larger systems over time. Astronomers continue studying the cosmic web using powerful telescopes and large galaxy surveys that map the positions of millions of galaxies across the sky. These maps reveal how galaxies cluster together and how the large-scale structure of the universe evolved over time. By examining these patterns, scientists gain insight into how gravity, dark matter, and ordinary matter work together to shape the universe. And as we continue drifting through this immense cosmic network, we begin to notice that galaxies not only grow through mergers and gas flows, but also transform through powerful events that can dramatically change their structures across cosmic time.
As galaxies continue evolving within the vast structure of the cosmic web, their growth is influenced not only by the material they gather, but also by the energy produced within them. Over billions of years, powerful processes inside galaxies can reshape their structure, alter their star formation, and sometimes even change their entire appearance. One of the most dramatic influences comes from massive stars. These stars live fast and burn their fuel at incredible rates. Because of their large mass, their lifetimes are relatively short compared with smaller stars like our Sun. After only a few million years, many of these massive stars end their lives in powerful explosions known as supernovae. A supernova releases enormous amounts of energy into the surrounding space. For a brief moment, the explosion can shine as brightly as an entire galaxy. The shock waves produced by the explosion move outward through nearby gas clouds, heating and compressing the gas as they travel. These shock waves can trigger new waves of star formation by squeezing nearby gas into dense regions where gravity takes over. In other cases, the energy can push gas outward, dispersing the material that would normally collapse into new stars. Because of this, supernova explosions can both create and suppress star formation, depending on the conditions around them. Supernovae also play a crucial role in enriching galaxies with heavier elements. Inside massive stars, nuclear reactions create elements such as carbon, oxygen, silicon, and iron. When the star explodes, these elements are scattered into the surrounding gas. Over time, these enriched gases become part of new generations of stars and planets. The iron in our blood, the oxygen we breathe, and many of the elements that make up our world were originally formed inside stars that exploded long before our solar system existed. In galaxies where star formation is particularly intense, thousands of supernova explosions may occur over relatively short periods of time. The combined energy from these explosions can drive powerful winds of gas outward from the galaxy. These galactic winds can travel far beyond the visible edges of the galaxy, carrying gas and newly formed elements into intergalactic space. In some cases, this outflow can remove a significant portion of the gas that would otherwise fuel future star formation. Because of these processes, galaxies are constantly exchanging material with their surroundings. Gas flows inward from the cosmic web, fueling new stars, while energetic events push some material outward again. Astronomers studying distant galaxies often detect evidence of these winds moving through intergalactic space. By analyzing the light from galaxies, scientists can measure how gas is moving and determine whether it is flowing inward or outward. These observations reveal that galaxies are not closed systems. Instead, they are dynamic environments where matter and energy circulate between galaxies and the larger universe. And as this long cycle continues across billions of years, galaxies slowly transform, gradually shaping the vast and intricate cosmic landscape we observe today.
As galaxies exchange matter with their surroundings, another subtle process quietly shapes how they grow and evolve. This process involves the steady flow of gas moving through the cosmic web and feeding galaxies over enormous periods of time. While dramatic galaxy mergers often capture our imagination, much of a galaxy's growth may actually occur through these slower, continuous streams of gas. Across the universe, vast filaments of dark matter stretch between galaxy clusters like invisible highways. Along these filaments, clouds of hydrogen gas drift slowly through space. Gravity gently guides this gas toward galaxies that lie along the filaments, allowing them to gather fresh material over time. When this gas reaches a galaxy, it can settle into the galaxy's rotating disk. There, it cools and forms new clouds where stars may eventually ignite. This steady supply of gas acts like a long-term fuel source, allowing some galaxies to continue forming stars for billions of years. Astronomers sometimes refer to this process as cold gas accretion. Unlike the violent bursts of star formation triggered by galaxy collisions, cold accretion is much quieter and more gradual. Yet over long stretches of time, it can provide a significant portion of the material that galaxies use to build new stars. Observations suggest that this type of gas flow was especially important during the early universe. At that time, galaxies were smaller and surrounded by abundant streams of gas flowing along the cosmic web. These steady inflows may have helped young galaxies grow rapidly during their early stages of development. However, not all of the gas that approaches a galaxy becomes part of it. Some gas may become heated as it falls toward a galaxy's gravitational field.
When gas becomes too hot, it can remain suspended in a large halo surrounding the galaxy, rather than settling into the disk where star formation occurs. These halos of hot gas are difficult to observe directly because they emit only faint radiation. But through careful observations using X-ray telescopes, astronomers have detected evidence of these extended halos surrounding many galaxies. The presence of these halos reveals another layer of complexity in galaxy evolution. Some galaxies receive steady flows of cool gas that allow them to continue forming stars, while others become surrounded by hot gas that prevents fresh material from reaching their disks. This difference may explain why some galaxies remain active star-forming systems for long periods of time, while others transition more quickly into quieter states where star formation slows down. By studying how gas flows into and around galaxies, astronomers are gradually uncovering the delicate balance between growth and stability in the universe. Galaxies are constantly interacting with the larger cosmic environment, drawing in new material while also releasing energy and gas back into space. And as these slow cosmic currents continue shaping galaxies over billions of years, they help create the incredible diversity of galaxy forms we observe across the universe today.
As astronomers continued studying galaxies across different distances and times, they began to realize that galaxies follow long and complex life cycles. Some galaxies remain active for billions of years, continuously forming new stars from incoming gas. Others slowly exhaust their fuel and settle into quieter states where star formation becomes rare. Understanding why these differences occur has become one of the central questions in modern astronomy. Part of the answer lies in the balance between the gas entering a galaxy and the energy that pushes gas away. In many galaxies, gas flowing inward from the cosmic web provides the raw material needed to create new stars. When this gas cools and settles into dense clouds, gravity can compress it until nuclear fusion begins. New stars ignite, lighting up the galaxy with clusters of brilliant blue light. But as star formation continues, powerful forces begin to build inside the galaxy. Massive stars produce intense radiation and strong stellar winds that push against nearby gas clouds. When these stars eventually explode as supernovae, the energy released can heat surrounding gas and drive it outward. At the same time, activity near the galaxy's central black hole can also release tremendous energy. Jets and radiation from the black hole can disturb gas across large regions of the galaxy, sometimes pushing it out of the galaxy entirely. When enough gas is heated or expelled, the supply needed for star formation becomes limited. Without fresh gas collapsing into dense regions, the galaxy's star formation gradually slows. This delicate balance between incoming gas and outgoing energy determines how long a galaxy remains active. If gas continues flowing inward, the galaxy can keep producing new stars for extended periods. But if powerful feedback processes remove or heat the gas, star formation can eventually shut down. Astronomers refer to these energy-driven effects as galactic feedback.
Feedback plays a crucial role in regulating galaxy growth. Without it, galaxies might form stars far too rapidly, using up their gas supplies much earlier in the universe's history. Instead, feedback helps maintain a balance that spreads star formation across billions of years. It prevents galaxies from growing too quickly, while also shaping their internal structures. Observations of distant galaxies provide important evidence for these processes. Some galaxies appear surrounded by enormous outflows of gas moving away from their centers. Others show signs of inflowing gas streams that continue feeding new star formation. By studying these flows of matter and energy, astronomers are learning how galaxies maintain equilibrium between growth and stability. Over the lifetime of the universe, these processes have helped produce the wide variety of galaxies we see today. Some galaxies remain vibrant and active, glowing with young stars and swirling clouds of gas. Others have entered quieter stages where most star formation has ended. And yet, even the calmest galaxies still carry the memory of the energetic forces that shaped them long ago, written into the stars that continue shining across the vastness of space.
As astronomers continued exploring galaxies across vast stretches of cosmic time, they began to notice that galaxies not only change internally, but they also influence the space around them. The material that flows outward from galaxies does not simply disappear into the darkness. Instead, it becomes part of the wider environment between galaxies, slowly enriching intergalactic space with elements created inside stars. In the earliest universe, most of the matter in space consisted of simple elements such as hydrogen and helium. These elements were formed shortly after the universe began expanding. At that time, heavier elements like carbon, oxygen, and iron did not yet exist in large amounts. Those elements were gradually created inside stars. Through nuclear fusion, stars forged heavier atoms in their cores while they burned their fuel. When massive stars reached the end of their lives, many exploded as supernovae, scattering these newly formed elements outward into space. Over billions of years, these explosions enriched the gas surrounding galaxies. Some of this enriched gas drifted away into the intergalactic medium, the vast space between galaxies. Other portions of the gas later fell back into galaxies, becoming part of new generations of stars. Because of this cycle, the universe slowly became more chemically complex as time passed. Each generation of stars contributed new elements that allowed future stars and planets to form with increasingly diverse compositions. This gradual enrichment plays an important role in shaping galaxies. Gas that contains heavier elements cools more efficiently than pure hydrogen gas. When gas cools, it can collapse more easily under gravity, forming dense clouds where stars ignite. As a result, later generations of stars often formed under different conditions than the earliest stars in the universe. Their compositions included elements produced by earlier stars, allowing for the formation of planets and more complex cosmic structures. Astronomers study the chemical compositions of galaxies by analyzing the light they emit. Different elements leave distinct signatures in the spectrum of a galaxy's light. By measuring these spectral lines, scientists can determine which elements are present and in what amounts. These measurements allow astronomers to reconstruct the chemical history of galaxies across cosmic time.
Younger galaxies in the distant universe often show simpler compositions, dominated by lighter elements. Nearby galaxies, which have experienced billions of years of star formation, tend to contain much richer mixtures of heavier elements. This chemical evolution reveals another layer of the universe's long story. Galaxies are not only collections of stars and gas, but also cosmic laboratories where new elements are continuously created and recycled. And as galaxies release material into the surrounding universe, they slowly transform the very fabric of cosmic space, spreading the ingredients needed for future stars, planets, and perhaps even life itself. As galaxies continued evolving over billions of years, astronomers began noticing that some galaxies seemed to age much faster than others. While certain galaxies remained rich with gas and continued forming stars steadily, others appeared to have stopped their star formation surprisingly early in cosmic history. These early aging systems are massive galaxies that formed large numbers of stars very quickly during the universe's younger years. In those early stages, they experienced extremely intense periods of star formation, rapidly converting huge clouds of gas into new stars. During these powerful bursts of activity, the galaxies consumed much of their available gas in a relatively short period of time. Massive stars formed in large numbers, and their energetic radiation and explosive deaths released tremendous amounts of energy into the surrounding gas. This energy heated the gas and pushed some of it outward, making it increasingly difficult for the galaxy to continue forming new stars. At the same time, the galaxy's central supermassive black hole may have become active, releasing additional energy that further disturbed the remaining gas. Together, these effects created conditions where the galaxy could no longer efficiently form new stars. Without a fresh supply of cool gas collapsing into dense clouds, star formation gradually came to a halt. Once this happened, the galaxy entered a long period of quiet evolution. The stars that already existed continued shining, but few new stars replaced them. Over time, the bright blue stars that had formed during the galaxy's active youth faded away, leaving behind older stars that glowed with softer, reddish light. Astronomers studying these galaxies often describe them as massive quiescent galaxies. They are large, bright systems filled with billions of stars, yet they show little evidence of ongoing star formation. Observations of distant galaxies have revealed that some of these quiescent systems already existed when the universe was only a few billion years old. This discovery surprised many scientists because it suggests that some galaxies formed and aged far more quickly than previously thought. Understanding how these galaxies shut down their star formation so early remains an active area of research. Some scientists believe that powerful feedback from black holes played a major role, while others think that environmental effects or rapid gas consumption may have been responsible. By studying these quiet giants across different periods of cosmic time, astronomers are gradually learning how galaxies transition from active youth to calm maturity. These galaxies remind us that the universe does not evolve at a single pace. Some systems grow slowly and steadily over billions of years, while others experience intense early activity, followed by long, quiet phases. And as we continue observing galaxies across ever greater distances, we begin to see how these different evolutionary paths combine to create the rich and diverse population of galaxies that fills the universe today. While some galaxies grow rapidly and then settle into quiet stages, others continue evolving through long sequences of interactions that reshape them again and again. One of the most important of these processes is the gradual merging of galaxies across cosmic time. In the early universe, galaxies were much closer together than they are today. Because space itself has been expanding for billions of years, distances between galaxies have steadily increased. But long ago, galaxies often drifted within relatively crowded regions where gravitational encounters were common. When two galaxies approached each other, their gravitational forces began to pull and stretch their structures. Stars, gas, and dust responded to these tidal forces, sometimes forming long streams that extended far beyond the original galaxies. These tidal tails could stretch across hundreds of thousands of light years, creating beautiful arcs of stars and gas that trace the motion of the interacting galaxies. Over time, the galaxies would continue orbiting each other, losing energy through gravitational interactions. Eventually, the galaxies could merge into a single system. During this merger, their stars passed by one another with very little direct collision because the distances between stars are enormous. However, their gas clouds behaved very differently. Gas clouds are far more likely to collide and compress during a merger. When these clouds collide, they can collapse into dense regions where new stars ignite in large numbers. This often triggers powerful bursts of star formation that light up the merging galaxies with bright clusters of young stars. The result is sometimes known as a merger-driven starburst, where star formation briefly becomes extremely intense. Over time, the merged system begins to settle into a new structure. The original disks of the galaxies may be disrupted, and the stars can move into more randomized orbits. In many cases, this process eventually produces a large elliptical galaxy. Astronomers have captured stunning images of galaxies in various stages of merging. Some show two galaxies connected by glowing bridges of stars. Others display enormous tidal tails extending into space like delicate ribbons of light. These images reveal that galaxy mergers are not sudden events, but long, slow dances that unfold over millions or even billions of years. Even our own Milky Way is not immune to these processes. In fact, astronomers have discovered that the Milky Way is slowly approaching another large galaxy known as Andromeda. Although the two galaxies are still separated by millions of light years, gravity is gradually drawing them closer together. In several billion years, they are expected to begin a long merging process that will eventually reshape both galaxies. This future event reminds us that galaxy evolution is ongoing. The universe continues changing, and the galaxies we see today will look very different in the distant future.
As astronomers observe galaxies across immense distances, they often encounter a surprising mixture of ages and structures within the same region of space. A single telescope image can contain galaxies that appear mature and organized, alongside others that still look chaotic and unfinished. This happens because the universe itself acts like a layered timeline. Light from nearby galaxies has traveled for a shorter time before reaching us, so those galaxies appear more evolved. Their structures may include stable spiral arms, well-defined disks, or smooth elliptical shapes formed after long histories of mergers and interactions. But in the same image, a galaxy located much farther away may appear much younger. Its light began traveling billions of years earlier, when the universe was still in a different stage of development.
Because of this, astronomers often describe deep sky images as snapshots containing multiple eras of cosmic history at once. This ability to see different stages of galaxy evolution in a single observation is incredibly valuable. Scientists can compare galaxies that existed at different times without needing to travel through space themselves. The universe provides its own record simply through the time it takes for light to reach us. In many deep field observations, astronomers notice that distant galaxies frequently appear smaller and less structured than nearby ones. Some resemble bright knots of star formation, connected by faint streams of stars and gas. Others appear irregular, with no clear spiral arms or symmetrical shapes. These early forms suggest that galaxies gradually become more organized as they evolve. Over time, repeated mergers, rotating disks of gas, and the influence of gravity help shape galaxies into the structures we commonly see in the nearby universe. Yet the process is not always simple or predictable. Some distant galaxies already display surprisingly organized structures, even when the universe was relatively young. Observations have revealed spiral galaxies existing earlier than many scientists once expected. These discoveries suggest that galaxy formation may sometimes proceed more quickly than earlier models predicted. In certain conditions, gas may settle into rotating disks rapidly, allowing spiral patterns to emerge sooner than previously believed. Astronomers continue studying these early spiral galaxies to understand how such organized structures could form within a universe that was still crowded with frequent interactions and mergers. The more we observe distant galaxies, the clearer it becomes that galaxy evolution follows many different paths. Some galaxies grow gradually and remain relatively stable for long periods. Others undergo repeated collisions that dramatically reshape their structures. Even the quietest galaxies today may carry the scars of ancient interactions hidden within their halos of stars. As we keep exploring deeper into space, the universe continues revealing these layered stories of growth and transformation. And with each new observation, we come closer to understanding how countless galaxies across the cosmos slowly assembled themselves into the vast cosmic landscape we see today.
As astronomers gather more detailed observations of distant galaxies, they begin to understand that galaxies are not only shaped by internal processes and mergers, but also by the long passage of cosmic time itself. Over billions of years, gravity steadily organizes matter, while energy from stars and black holes slowly reshapes the environments around them. One of the most remarkable aspects of galaxy evolution is how gradually these enormous systems change. The processes involved often unfold across millions or even billions of years, far longer than any human lifetime. Yet, by observing galaxies at many different distances, astronomers can piece together a sequence of stages that reveals how galaxies transform. In the early universe, galaxies were often smaller and filled with turbulent clouds of gas. Star formation could occur rapidly, producing bright clusters of young stars that lit up their surroundings. These galaxies frequently interacted with nearby neighbors, leading to collisions and mergers that combined smaller systems into larger ones. As time passed, many galaxies began to settle into more stable forms. Gas that had once been chaotic gradually organized into rotating disks.
Stars followed predictable orbits within these structures, creating the graceful spiral arms that we see in many nearby galaxies today. Other galaxies followed different paths. Repeated mergers could disrupt their disks entirely, causing stars to move in random directions rather than along orderly rotations. Over time, these systems often became elliptical galaxies with smooth, rounded shapes. Throughout these transformations, galaxies continued exchanging matter from their surroundings. Gas flowed inward from the cosmic web, fueling new star formation. At the same time, powerful winds from supernova explosions and active black holes pushed gas outward into intergalactic space. These ongoing exchanges gradually shaped both the galaxies and their environments around them. Material expelled from galaxies enriched the surrounding gas with heavier elements, while fresh streams of gas continued feeding new generations of stars. Astronomers studying these processes often describe galaxy evolution as a balance between growth and feedback. Galaxies gather matter from the universe, convert that matter into stars, and then release energy that influences future star formation. Because these cycles repeat across billions of years, galaxies slowly transform into the systems we observe in the present-day universe. Some remain vibrant star-forming galaxies, glowing with young blue stars and swirling clouds of gas. Others have become quieter systems, dominated by older stars. Each galaxy carries the record of its own long journey through cosmic time. Its structure, color, and motion reveal the many events that shaped it across billions of years. And as astronomers continue observing galaxies at ever greater distances, they are gradually uncovering the full story of how these vast systems formed, evolved, and spread across the immense expanse of the universe.
As our exploration of distant galaxies continues, one of the most comforting realizations is how interconnected everything in the universe truly is. The galaxies we observe across billions of light years are not isolated creations. They are part of a shared cosmic story that began with the earliest expansion of the universe and continues unfolding even now. Every galaxy we see carries the marks of gravity, time, and energy working together across unimaginable scales. The stars inside them are constantly evolving, quietly transforming hydrogen into heavier elements. When those stars reach the ends of their lives, they return their material to space, allowing new stars and planetary systems to form from the recycled matter. This ongoing cycle of creation and transformation is one of the universe's most enduring patterns. Galaxies gather gas from the cosmic web, convert that gas into stars, and then release new elements back into space through stellar winds and supernova explosions. Over billions of years, this process gradually enriches the universe with the ingredients needed to build more complex structures. Planets form around younger stars. Some of those planets may develop oceans or atmospheres, and in rare cases, the right conditions might even allow life to emerge. When we look at distant galaxies, we are not only observing remote objects in space, we are witnessing earlier chapters of the same cosmic process that eventually led to the formation of our own solar system. The Milky Way itself was shaped by many of the same forces we see in distant galaxies today. It gathered gas from the cosmic web, merged with smaller galaxies, and formed countless generations of stars over billions of years. Even now, our galaxy continues evolving. New stars are born within vast clouds of gas and dust scattered throughout the Milky Way's spiral arms. At the same time, older stars drift through the galaxy, carrying with them the chemical history of earlier cosmic eras. By studying distant galaxies, astronomers are essentially studying the universe's memory. Each galaxy represents a moment in time, revealing how cosmic structures gradually assembled and changed. These observations remind us that the universe is not static. It is a dynamic system where matter moves, stars ignite and fade, and galaxies slowly reshape themselves across immense stretches of time. And as our telescopes become more powerful, we are able to observe galaxies that formed closer and closer to the universe's earliest moments. With each discovery, the picture of cosmic history becomes clearer. And as we prepare to drift into the final stage of our quiet journey through distant galaxies, we begin to see the universe not as a collection of separate objects, but as a vast and continuous story written across the stars.
As our gentle journey through distant galaxies slowly comes to an end, it becomes clear that the universe is far more vast and interconnected than it first appears when we glance at the night sky. Those faint points of light scattered across the darkness are not simply distant stars. Many of them are entire galaxies, each containing billions or even trillions of stars, quietly shining across the immense depths of space. Every galaxy we have imagined tonight represents a chapter in the universe's long history. Their light has traveled unimaginable distances before reaching us, carrying messages from eras long before our planet existed. When that light finally arrives at our telescopes, it allows us to see the universe not just as it is today, but as it once was billions of years ago. In those ancient times, galaxies were still gathering the materials needed to grow. Clouds of hydrogen gas collapsed under gravity to form the first generations of stars. Those stars lived brilliant lives and eventually returned their elements to space through powerful explosions. Over time, these elements became part of new stars, planets, and complex structures. Slowly and patiently, the universe built the ingredients necessary for the rich cosmic landscape we observe today. Galaxies themselves continued changing throughout this long history. Some grew through quiet flows of gas drifting along the cosmic web. Others expanded through dramatic mergers with neighboring galaxies. Inside them, stars were born, lived out their lives, and enriched the surrounding space with new elements. At the centers of many galaxies, supermassive black holes quietly shaped their surroundings, sometimes igniting brilliant activity that could outshine the entire galaxy itself. Yet despite all these powerful forces, the universe also contains an incredible sense of calm. Across billions of light years, galaxies drift slowly through space, following the gentle pull of gravity. Their stars orbit steadily, and their light travels silently across the cosmos. When we look at distant galaxies, we are witnessing this immense balance between motion and stillness, between change and stability. The same cosmic processes that formed distant galaxies also shaped our own Milky Way. The atoms that make up our world were once created inside ancient stars, scattered into space, and eventually gathered again to form new systems. In this way, every galaxy we observe is connected to our own story.
And perhaps that is the most peaceful thought of all. The universe is not simply a distant place filled with unfamiliar objects. It is a vast, ongoing story of matter, energy, and time, a story that eventually led to the formation of stars, planets, and the quiet moment you are experiencing now. So as the night sky stretches quietly above, those distant galaxies continue shining patiently across space, and their ancient light will keep traveling, gently illuminating the universe for billions of years to come.